Okay, for topic 2, we're going to look at multiplying radical expressions with more than one term. So we've already talked about the product rule for radicals. The product rule for radicals allowed us to multiply single term radical expressions. And just in case you forgot, the product rule states, so we have the product rule for radicals. This is different than the product rule for exponents. This is the product rule for radicals. It tells us that if I have the square root of a times the square root of b, I could write that as the square root of a times b. You can merge things under a single radical if they have the same index. So this would apply for a cube root, a fourth root. You just have to have the cube root of something times the cube root of something. You can merge it under a single cube root symbol, okay? Similarly, if you have a single square root or cube root or nth root, you can break it apart. Now, for us, we're mostly going to focus here. This is what we're going to be looking at in this particular video, okay? Now, two other things we need to remind ourselves actually apply to polynomials, but the same principles will work here. So we learned the distributive property and the FOIL method when we're working with polynomials, but the exact same process can be kind of used here when we're dealing with these radical expressions. Remember, we treat the radical like a variable at first. It's not a variable at all, but we can treat it like a variable. So that allows us to use this distributive property and the FOIL method. So remember the distributive property. It says if you're multiplying something in parentheses by a single term, you can just move that thing outside the parentheses through the parentheses. So you can multiply through addition or you can multiply through subtraction. So if I had something like a outside parentheses times in parentheses b plus c, I could take a times b and then add it to a times c. The same thing works with subtraction. Now, the FOIL method was specifically for multiplying binomials. So remember, that's kind of in the world of polynomials, which was a previous chapter, but the same process applies here. If you have two sets of parentheses and each set of parentheses has two terms, you can do basically the equivalent of the FOIL method. So you take the first term in the first set of parentheses and distribute it in turn through the second set of parentheses. You then come back and get the second term in the first set of parentheses and then distribute that through the second set of parentheses. And everything kind of simplifies down. Sometimes nicely with radicals, sometimes not, but the same process works. Just distribute everything is kind of how it fizzles out, we'll say. Okay? So let's look at example 2. Example 2 just tells us to multiply. Well, in part A, I have a single radical expression times the difference of two expressions. So here we would want to use the distributive property, okay? And if you're just taking a single radical and multiplying it by just a constant, you just tack the two things together. Remember, a lot of times we treat these radical expressions like they're variables when we're performing operations on them. Keep in mind, a radical expression is not necessarily a variable unless it contains a variable, but we still treat it like a variable. So in part A, I'm going to treat the square root of 5 like I would an x or a p or a z. Okay, I'm going to treat it like a variable initially, and then we'll simplify things down if necessary. So when I have the square root of 5 times 3, I just want to write that as 3 times the square root of 5. Then when I take the square root of 5 and multiply it by -4, I'm going to get kind of like 1 square root 5 times 4 square root 5. Well, 1 times 4 is 4, so we get -4. And then the square root of 5, just multiply the two of them. So I have the first square root of 5 times the second square root of 5. And this is where we can apply the product rule for radicals, okay? 3 square root 5 is just going to be 3 square root 5 for now. -4 is just going to be -4. But the square root of 5 times itself can be pushed under one radical. And if you go over here to the side and think about this, well, the square root of 5 times 5 is just the square root of 25, which is just 5. So if you take a square root and multiply it by exactly itself, you're just left with the radicand, okay? Because technically what we're doing is if we have the square root of 5 times the square root of 5, that's the square root of 5 squared, and we know a square root and an exponent of 2, they're inverses. They just undo each other. So you're just left with your radicand. So be on the lookout for something like that. Now, if you didn't see that initially, like if you weren't aware that that rule could work for the square root of 5 times itself, go ahead and use the product property or the product rule for radicals, push everything under one radical, and then simplify it. So I get 3 square root 5 minus 4 times the square root of 5 times itself, which is just 5. So I get 3 square root 5 minus 20. And that's it. Let me fix my 5. It looks kind of crazy. And there you have it. You could check something like this on the calculator. I do want to be really clear. When I go and show you things on the calculator, it's just to prove that the first expression really equals our end result expression. You are not permitted to go to your calculator here and then spit out some crazy decimal answer for your instructor. That's not how this works. We want to simplify the radical expression. We want to maintain a radical expression. We want it to be exact. And if you go to the decimal form and then round it, it's no longer exact. This is exact. If I go to the calculator, I get a rounded version of that, okay? So anytime I've shown you stuff on the calculator, we're just proving things work. You really do have to simplify, leaving your radical expression intact, or simplify it to an integer if it comes to that, okay? Let's look at part B. So for part B, we have two expressions that have two terms each. So this looks very much like two binomials. Again, they're not binomials because this isn't a polynomial expression, but they work the same way. So I'm going to start with this 2 in the first expression, and I'm going to distribute it through the second expression. So I start with 2 times 5, and then I've got 2 times 4 square root 3. So what I want to do here is kind of treat the square root of 3 like a variable. It's not, we're just treating it like one. So I would take the 2 times 4 and multiply those. That gives me 8, and then just leave the square root of 3. We'll deal with that later if it simplifies down. Now we're done with the 2 right here. So we've kind of already distributed that. Now we want to pick up the -7 square root 3 and distribute that. So -7 square root 3 times 5, I want to take the -7 and the 5, and I want to multiply those. That gives me -35. And then I just tack on the square root of 3. So I've got -35 square root 3. And then finally, I want to take -7 square root 3 and multiply it by 4 square root 3. So I want to take those coefficient pieces, those constant factors, the -7 and the 4, I want to multiply those first. That gives me -28. And then I've got square root 3 times square root 3. So let's see if we can do some simplifying. I see 3 things we can do right off the bat. So first of all, 2 times 5 is just 10. So that's easy. 2 times 5 is 10. Now, when I look at the middle 2 terms, I have 8 square root 3 minus 35 square root 3. Those are called like radicals. We talked about that in the previous video. So like radicals can be combined. We treat the radical expression like a variable. It is not a variable, but we treat it like one. So we want to take those constant factors out front, the things that look like coefficients, and we want to add them or subtract them. So I have +8 minus 35. That would give me -27 square roots of 3. So I've combined those two radical expressions into a single one. And then finally, I have -28. So I've got -28 here. But then when we look at this right here, well, this is really just the square root of 3 squared, right? We have the square root of 3 times itself, and a square root and an exponent of 2, they undo each other. So the square root of 3 times itself becomes just plain old 3. So this is times 3 right here. If you don't see that, push it all under one radical using the product rule, okay? We would get the square root of 3 times 3, which is the square root of 9, which is 3, okay? Now we need to do a little more simplifying. -28 times just plain old 3, I can do that. So I've got 10 minus 27 square root 3 minus, well, let's see, 28 times 3 I think is 84. Let me double check. Yes, we get -84. And then I have these two non-radical pieces that I can combine. So 10 and -84, they're not radical expressions. They're just plain old integers. So I can simplify that. So I get 10 minus 84 is -74 minus 27 square root 3. So again, you cannot just go to a calculator and type in 2 minus 7 square root 3 times 5 plus 4 square root 3 and think that's acceptable. You'll get a rounded decimal answer. We want the exact answer. And for it to be exact, we need it simplified with radicals still in the expression. Okay? Now, part C, we talked about stuff like this again when we were dealing with polynomials. And even though these are not polynomials, a lot of those rules apply. If I had something like a plus b quantity squared, that was equal to a plus b times a plus b, and then I would have to FOIL, okay? Same thing's happening here. This is really the square root of 7 minus 3 square root 2 times itself. And we would need to do that FOIL method. We're going to do that same process of distributing twice. So I'm going to start with the square root of 7. Well, the square root of 7 times itself is just the square root of 7 times square root of 7, but it's really the square root of 7 squared. So this is going to simplify down to just plain old 7, okay? Now I have the square root of 7 times -3 square root 2. So that's -3 square root 7 times square root 2. We'll simplify in just a moment. I now have to come back. I'm done with this term right here. I'm going to come back and pick up -3 square root 2 and distribute that, okay? So -3 square root 2 times square root of 7 is -3 square root 7 times square root 2. And then finally, -3 square root 2 times -3 square root 2. I can multiply the -3's, so that gives me +9 square root 2 times square root 2. Whew, that's a lot, right? Lots of square roots. It's a mouthful. Okay, we already know the square root of 7 times itself is the square root of 7 squared, which means the square root and the exponent of 2 undo each other, so we're just left with 7. Right here in the middle, we need to do a little work. This is -3 square root 14 minus 3 square root 14. We can use that product rule for exponents and take the square root of 7 and the square root of 2 and push them under a single radical, okay? And then we have +9 times, well, the square root of 2 times itself is the square root of 2 squared, which is really just 2, so we get 9 times 2. Got to do a little more simplifying. So 7 is just 7. But then right here, -3 square root 14 minus 3 square root 14, those are like radical expressions. We can take -3 and subtract 3, and then just leave the variable, leave the radical portion alone. So we get -6 square root 14. And then don't forget your +9 times 2 or +18. So one more thing, we have two terms that are not radicals. We want to go ahead and combine those. So 7 plus 18 is 25. And then just tack on the -6 square root 14. So definitely a little bit of work. Multiplying radicals is not difficult, but it is something you need to be very neat and organized with. Okay, there's lots of little pieces, and each of those little pieces really matters. So nice and slow, show your work, don't try to skip steps. Okay, so that is multiplying radical expressions with more than one term.